Bismillahirrahmanirrahim. Today we'll start talking about the EIGRP, Enhanced Interior Gateway Routing Protocol. So as a historical part, the EIGRP, or the Interior Gateway Routing Protocol, has been developed in 85 to overcome the limitations of RIP in terms of using the hop count. So IGRP was originally released to address the inaccuracies related to using the hop count as a metric for routing. Later on, the EIGRP was released in early 90s to overcome the problem related to the classful routing. So EIGRP deals with classless routing, in addition to some enhancements related to the route updates, which we have discussed before and we'll discuss it again today. So IGRP and as a result EIGRP, they use 4 different parameters as metrics. Okay, they use a combination of 4 different parameters: the bandwidth and delay, and these are offline parameters. So bandwidth is the if you have like so if you have a full path, you have router 1, and then you have router 2, and then you have router 3, and so on. Okay? So the bandwidth of the end-to-end route is the lowest bandwidth on any of these links. Okay? So the end-to-end bandwidth is the lowest bandwidth on any link across the route. Okay, the delay is the accumulated delay end to end. So the bandwidth is the bottleneck. Bandwidth is bottleneck parameter, which means that the end to end bandwidth is always like you have a bigger pipe and smaller pipe and bigger pipe and so on. So your limit is the smallest size pipe, right? But the delay is accumulative, which means that the end-to-end delay is the delay on this link, and then on this link, and then on this link, and so on. IGRP was discontinued in terms of support in these versions, which is not important to know. What we need to know now is that those are offline parameters, which means that bandwidth and delay are based on the characteristics of the link, the bandwidth of the link itself. So if the link, for example, is ADSL, then the bandwidth is well known before you start the network. Delay is also an offline parameter. It's calculated based on, of course, the theoretical bandwidth of the link, but the difference is that the delay is a cumulative parameter. On the other side, reliability and load depends on real-time information. Reliability and load depend on real-time information. So when you start running the network, the bandwidth of the link is different from the current load. The bandwidth is like a fixed characteristics about the link. Okay? But the load is the real-time load at this point in time. We know the difference, we see the difference. The load is the current load depending on how much traffic is currently going on. But the bandwidth is like a fixed parameter. It depends on whether this is a T1 connection, this is ADSL connection, this is whatever. Leased line, 3G, wireless, whatever. Okay, so that's the difference between offline parameters and real-time parameters. EIGRP has more complicated format compared to RIP, compared to Routing Information Protocol. So we need to really focus because it's gonna get a little bit complicated. So EIGRP uses message format, which is يعني, at a high level it's similar to RIP. So you have data link layer header. So you have the header which contains the physical address of the routers. You have the IP packet header, and as we will see later, EIGRP does not only support IP, it supports some other network level protocols like IPX and AppleTalk and whatever. Okay? And then we have the EIGRP packet header. Okay? So we need to be accurate here that if you remember in RIP, there was something here in the middle, which is the UDP header. Okay, which indicates that EIGRP does not use UDP. So this is one main characteristic in EIGRP, that it uses its own transport layer protocol to send the routing information. So I'm expecting to see some transport layer information as part of this header. So it does not use UDP, it does not use TCP. So we have to know whether this is reliable or unreliable, and how and what type of routing, what type of the transport layer protocol EIGRP uses, which we will talk about in a minute. And this is, of course, the payload of EIGRP. And as we will see here, the payload again is a little bit complicated. It's not just as in the case of RIP, we need to communicate what? We need to communicate the metric, right? And the destination. So for this destination, you have this distance. That's it. Here we have 5 different types. So for EIGRP, we have different types when it comes to the payload. Okay. So those are the 4 different high-level parts of the EIGRP message format. The first 2 parts are straightforward, so we're not going to go through the data link layer header or the IP header, because these are discussed in 455, and we're not going to discuss that here. So what we need to discuss here is the EIGRP packet header and what we call the TLV, or the type length value header. So first, EIGRP packet header contains 2 important fields, which is the opcode. The opcode or the operation code field. The opcode field indicates 5 different types. It's not like RIP. In RIP, we said that we use request and reply, and that's it. Here we have 5 different types. And also the autonomous system number. So we all know what the meaning of autonomous system. Okay, so autonomous system as a concept talks about or represents the group of routers which are controlled by a single authority. However, the autonomous system number is totally different. The autonomous system number as a field in the packet header indicates the EIGRP process ID. Okay, the EIGRP process ID. So what happens is, when we talked about RIP, we run one process okay, on each router to represent the rep to exchange the routing information automatically between the routers. However, for EIGRP, the router runs in general multiple instances of the EIGRP process. It runs in general multiple instances. So when you run multiple instances, you need to give each one a specific ID in order to identify that process. Okay? The reason for this is the fact that EIGRP can deal with multiple network level protocols concurrently. This is one of the reasons. Okay? So EIGRP can deal with multiple network level protocols concurrently. It can deal with IP, it can deal with IPX, can deal with AppleTalk, and so on. So in order for me to distinguish these processes, they use the autonomous system number. So autonomous system number here does not indicate the autonomous system that we know. So the name here, remember that the name here is a little bit misleading. So remember that the autonomous system number here indicates the EIGRP process ID and not the autonomous system number that we know. So the operation code and the autonomous system number. As you can see, there are some other fields, like the flag, the sequence. So you have flag, you have sequence, you have acknowledgement. What does this indicate to you? Yeah, bravo عليك. But it indicates first, before that, it indicates that it uses some kind of transport layer protocol of its own. Okay? And the fact that there is acknowledgement here indicates, yes, what you said, that it supports reliable communication. Unlike REP, which supports only unreliable, because it uses UDP. So this is one fundamental or big difference between REP and EIGRP. So it uses flags, sequence number, acknowledgement, checksum. So these are similar to TCP, right? But it does not use TCP per se. It uses its own transport layer protocol, which we will talk about later. And we have EIGRP parameters. So there is the TLV. This is called the TLV, or the payload of EIGRP. The payload contains 3 different types of messages. The first one is what we call the EIGRP parameters. Okay. The second one, which we will talk about in the next slide, is called the IP internal routing information, and we have IP external routing information. So in the payload that contains the EIGRP parameters, what happens is that, as we said, we use a matrix which is a combination of 4 parameters, right? So the EIGRP parameters communicate to other routers, communicate through the network. What parameters are used to calculate the matrix? So, as an example, we don't have to know exactly the equation. We may talk about it later, but as a concept, I can use a matrix which is which is combined of bandwidth, and as we said, delay, and as we said, reliability, and load, right? So we have those 4 parameters. So in order to combine them, I have to use some equation. So what happens is that they use weights K1, K2, K3, and K4, and they use summation to combine all the four parameters. Okay. So bandwidth and delay, these are some variables that that the router can discover or can calculate easily. But we need to communicate this case, because the routers, they have to agree on these weights in order to unify the calculation of the metric. Otherwise, one router will calculate the metric in a different way from other router, and we end up with different calculations for the metric. So these parameters need to be communicated to other routers. However, bandwidth, delay, reliability, and load, these are something that I can calculate locally. Okay? So, so that's what we have in the first TLV type, which is the EIGRP parameter. So the router needs to communicate K1, K2, K3, K4, and K5. K5 is not used. And what we call the hold time. The hold time here, remember that the hold time is different from the hold down timer that we have discussed before. Okay? So you need to really focus, because there is some overlap between the terminology, so you need to really be accurate here. So the hold time is the amount of time a router has to wait before it declares its neighbor not existing. Okay? So in other words, as we will talk about in a minute, EIGRP promotes the fact that the routers need to communicate hello messages continuously. And that's something that REP did not support before. And the reason for this is that you need to have a table which stores all your neighbors and the state of each neighbor, whether this neighbor existing currently or it's down, it's up, it's working, so and so on. Okay? Why we didn't have to do that in RIP? Because RIP uses periodic broadcast updates. Here, we support partial bounded updates, right? So we can send partial update to a specific router. So in order to send to a specific router, you need to know who is alive and who is dead, right? So what happens is that routers need to exchange hello messages, which we will talk about in a minute. They exchange hello messages back and forth every 5 seconds. The whole time here is the time that they have to wait. If they do not receive any hello messages within that time, they declare this neighbor dead. Okay? So they remove or they change the state of that neighbor in the neighbor's table to be dead or not available. Okay? This is different from the hold down timer that we talked about before. Okay, so any question here? So the only thing we need to know about these parameters, the default mode for EIGRP, okay, combines only the bandwidth and delay. So it does not, this is the default mode, but the administrator may actually choose to incorporate the load and reliability as well. But the default mode is that K1 and K3 are 1 for the bandwidth and delay. K2 and K4 are 0, which indicates that the reliability and load are not part of the default mode. But the administrator may choose to include them.
The administrator decides that based on the application?
Exactly, based on the application. Any question so far? TLV type, which is the EIGRP parameters. The other two types talk about exchanging real routing information. So first I have to communicate the parameters that I use in order to agree on these parameters. So that's how we will calculate the metric. This is the time that we need to wait in order to manage the neighbors. Okay, so the hello packets, if you don't receive the hello packets within a specific interval, then you declare the neighbor as down. The second TLV type is what we call IP internal fields. Okay, the IP internal fields is the main field that you communicate the routing information. Okay, so I expect here to find the destination. I expect here to find the metric, right, and so on. So the way EIGRP deals with that is that we see the metric field and the destination. We see here the metric and the destination, which used to be communicated in rep as usual, but we see here another field because here we're dealing with classless routing. So for classless routing, we need to communicate also the subnet mask. So this will get us will solve the problem of discontiguous networks, because now that we can communicate the subnet mask exactly, so we can deal with automatic summarization, we can deal with discontiguous networks, whatever, because now we can communicate the subnet mask. So so this field here contains the next hub, the delay, bandwidth, and these are some information that the router calculates, and of course if there is load, reliability, and so on. And the prefix length here, the prefix length is where you communicate the subnet mask. Okay, so like /24 or /16 or /17. So this is the prefix length. So the prefix length, because the subnet mask, as we said, it's a contiguous ones and then zeros, right? So you communicate here the number of ones. That's all you need to do. And the destination. Okay, so these are the fields you communicate as part of the IP internal parameters. So the most important thing is that we need to realize that in addition to the metric fields, which we have to communicate what bandwidth, delay, reliability, load, and so on, we need to also communicate the subnet mask field in a form of prefix length. And of course, we need to know the destination. The IP external field is the third TLV type, and this communicates the fields from an external autonomous system. So as we have discussed in the beginning of this part, that EIGRP works hand in hand with border gateway protocol. So EIGRP is internal routing protocol, of course, but it communicates with other exterior routing protocols like border gateway protocols. So exterior gateway protocol or exterior routing protocols, they deal with multiple autonomous systems, right? So if you actually receive information from another autonomous system and you try to put it in your routing table, EIGRP supports what we call IP external routing information. So in the external routing information, in addition to the normal information that we receive as part of the routing information, which again includes a load, reliability, bandwidth, and so on, and the destination, the subnet mask, and so on, similar to the internal. In addition to this, you need to communicate the external source, the originating routing, the originating router from the other autonomous system, the autonomous system ID, and so on. Okay? So that's for communicating external routing information from another autonomous system. Okay? So there is the internal one, which in that case, the router communicates to other routers only internal information within one autonomous system, and there is another TLV type for communicating or for receiving from an external autonomous system. And this happens if the router is what we call a designated router. If you remember, we said that a designated router has to support both the internal and the external, of course, right? So it gets information from the external autonomous system, and it also communicates information internally within that autonomous system.
So the parameter will exchange information between autonomous system within the same protocol. But the internal, each autonomous system only? Or
Yes. So the internal. Yes. So it's called internal gateway routing protocol. So the EIGRP is internal gateway routing protocol. So the mandate or the original function for EIGRP is to deal with the internal. Okay. However, if you receive information from another autonomous system, you need to only store the information where this external routing information came from. You don't have to calculate, like border gateway protocol deals with matrix and stuff as part of the entered autonomous system communication. EIGRP does not have to do that. It doesn't deal with matrix and stuff as part of the entered communication between autonomous systems. However, only internal. However, when it receives information from an external autonomous system, it just needs to store the fact that this information came from this originating router on this autonomous system. That's it. But it does not, as we will see, as we can see here, there's no metric or anything for EIGRP to calculate. For example, if I want to go from that autonomous system to an autonomous system like in China or whatever, where should I go?
all information, the ID and what first?
The autonomous system number, autonomous system ID, sorry, and the originating router on this, which is the designated router on the external autonomous system. Right? So it only needs to communicate and store this information, but it doesn't need to do any action or to calculate matrix or something like that, because this is the function of the border gateway protocol or the exterior routing protocol to calculate that if I want to go from this autonomous system to another autonomous system, where should I go? EIGRP does not deal with that, only internal. Okay? So, as we said before, EIGRP can deal with multiple network level protocols, not just IP, right? So, it supports what we call protocol dependent modules. So I can run one EIGRP process, okay, to deal with IP network layer protocol. And I can run another EIGRP process to deal with IPX or Apple Talk or whatever network level protocol that we have. Okay, so for each one, we have what we call protocol dependent module. It's just a new process. I spin off another EIGRP process to deal with a specific network layer protocol. Based on that, we need to have 3 copies of all the tables, or more, 3 or more, of course. 1 per network level protocol. So I have here, I have 1 neighbor table, because we said that we need to maintain the neighbors around each router. So each router has to store the neighbors. Okay. So I have 1 table For AppleTalk, one table for IPX, one table for IP. Okay. Similarly, for there is what we call the topology table. From the hello messages, we calculate, we discover all the neighbors. From these neighbors, we have to calculate what we call a topology, the topology of the network. Why? Again, because I need to understand the topology in order to send like partial updates to specific routers. So I need to know the topology of the system around me. And of course, the routing table. So one EIGRP instance will have one copy of the neighbor table, one copy of the topology table, one copy of the routing table. So this example here indicates that we have three different processes of EIGRP, three different protocol-dependent modules for EIGRP to deal with three different network level protocols, which are AppleTalk, IPX, and IP. Okay? Again, these are all complexities that REP did not have to deal with. But because of the fact that EIGRP deals with partial updates, deals with bounded updates, and so on, it needs to maintain all these complicated tables. Any question? Yeah, so this part as well we talked about. So as we said, EIGRP uses a specific transport layer protocol, which we call reliable transport protocol. Reliable transport protocol, of course, uses the fields in the EIGRP header, which we talked about, which is the acknowledgement and sequence and so on, in order to support both reliable and unreliable. Okay, so it supports both modes, and that's why EIGRP does not use TCP, because TCP supports only a reliable. But in that case, we need to be flexible, because there are messages that we will discuss later. There are some messages that we require reliable transmission, and there are some other messages that do not require reliable transmission. So the purpose of RTP used by EIGRP is to transmit and receive the EIGRP packets in reliable as well as unreliable mode. Not only that, this protocol also supports unicast and multicast. Because in general, as we said, when we use bounded updates, right? So we use partial updates, in which case we only communicate the changes that happens, right? Bounded updates meaning what? That we communicate it only to the routers that get affected by the change. So in order for me to send it only to a subset of routers, then I have to use a multicast. So I may actually send to one specific router, because this is the only router that that will get affected by the change, or a subset of routers. And of course, because you use multicast as a specific or a special case of multicast is broadcast. So if you want to use broadcast, then you can do multicast to all routers, basically. Okay, so the RTP uses reliable and unreliable, and chooses a unicast and multicast. Any question here? Do we have someone from Dr. Mazen's office? They requested to okay, خلاص. As we said, because the EIGRP uses partial and bounded updates, it needs to discover and maintain and manage the neighbors around it. Okay? And for that purpose, we use what we call a hello messages. So the hello messages, they get communicated in unreliable mode. Hello messages they get communicated in unreliable mode. When I send hello, I send it to all routers. I send it as broadcast, okay? And I expect to receive a reply which indicates that who is there and who is not. So for that, we use unreliable transmission. Okay? So it's used to discover and form the adjacencies. Adjacencies اللي هم neighbors يعني. And so if I do not receive hello messages from a router for a specific duration, which is the whole time, then I declare this router dead or not available. And I update the neighbors table accordingly. So the hello messages are unreliable messages. So that's one type of messages that we communicate. Another type, which is what we call the update packet. So the update packet is a triggered update. It's used for the triggered updates. If a router discovers a change in the network, like one network goes down, then it triggers an update. And the update contains what change has happened, and in general, it communicates that in a reliable mode using multicast. Okay? So I need to communicate that change only. That change only. So I don't have to again group all the routing information in the routing table and say, no, I need to communicate a specific change that happened at this point in time. And then I send an update message, which will have the fact that this network is currently down, and I send it using, in general, multicast. So I have to figure out which of these two routers will get affected by the change. In that case, in that particular case, both of them will get affected. So in which case, I have to send the change to both of them using multicast.
But will this help the protocol converge faster?
Yes, of course. This is one of the main characteristics of EIGRP. I think this is from Dr. Mazen's office. That it uses partial updates and bounded updates, in which case, it converges faster. So we'll stop here.